Coimbatore-based PSG and Sons Charities evolved a unique education and business model almost a century back. The four sons of the founder, Sri P.S. Govindaswamy Naidu, created a virtual fifth brother called Charity that has become the sprawling PSG empire, running not just several educational institutions but also manufacturing industries under the PSG umbrella. PSG and Sons Charities operates a state-of-the-art foundry at Neelambur, a suburb of Coimbatore. This 5-module video series, Inside a Modern Foundry, brings you various technical processes and specialized equipment that enable PSG Foundry to generate high-quality castings to meet customer demands across various industrial applications. In Module 1, an overview of the PSG business model was provided, along with the coverage of the pre-production foundry processes and pattern shop. Different types of patterns, pattern materials, and allowances that are provided were discussed. The dimensional aspects of patterns and the gauges and instruments used in pattern metrology were also presented. In this Module 2, we will be focusing on some of the remaining production processes that are an integral part of the overall foundry operations sequence, which enable the production of quality castings. 3 major topics are covered in this module. The first topic is foundry sand, which is very important in any foundry. PSG Foundry's modern sand plant details about composition, properties, and testing parameters of foundry sand are covered in this video, followed by the second topic, core making, that describes the core shop. Cores are like mini foundries in themselves, with their own sand and furnaces used for baking the cores. Cores are used when cavities or recesses are found in the final castings. The third topic is molding, which is the consolidation of all the other processes covered so far, that is pattern, core, and sand. The preparation of the molding line at PSG Foundry is done using a fully automated system. When all these elements come together, the stage is set for the actual melting and pouring the molten metal into the mold flasks, and these will be presented in subsequent modules. This 5-module video series on PSG Foundry will be a virtual tour into a modern foundry and explain its intricate technical processes.
PSG Foundry manufactures metal cast components for various applications in automotives, machine tools, textile, agriculture, motors and pumps. The Indian foundry industry produces the 4th largest volume of castings worldwide. About 100 million tons of molding sand are used annually for producing metal castings. Molding sand, also known as foundry sand, has been used as a molding material for centuries by Indian foundries. The molding sand primarily consists of clean, uniformly sized, high-quality silica sand that is bonded to form molds for ferrous metals such as iron and steel and non-ferrous metals such as copper, aluminium, brass and bronze. PSG Foundry has a wide range of equipment to cover all stages of the sand preparation such as cleaning, cooling, homogenizing, mixing and a complete in-line tower type sand plant for all the throughput capacities. The modern sand plant at the PSG Foundry consists of hoppers, cleaning stations, mixers, conveyors, intelligent control systems and all other associated subsystems that are required to meet day-to-day production targets. Conveyors such as belt conveyors, bucket elevators and screw conveyors are used to move molding sand from one location to another across the sand plant circulation system. This sand plant offers environmentally friendly operation with no loss of sand fines. Precise amounts of foundry sand and additives are fed simultaneously into the mixer through a single opening. Modern sand plants automatically carry out mulling, mixing and testing of the sand. They also reclaim used sand through magnetic separation to remove metal particles, crushing of lumps and finally remove excess fine sand, usually by washing in hot water or by mechanical impact. Robust design precision engineering and quality components combined with the latest process control technology to enable PSG Foundry to excel in preparing foundry sand both in terms of quantity and quality for producing superior quality castings. Sand casting is the most common casting process used in the foundry industry. Virtually all sand cast molds for ferrous castings are green sand. Foundries purchase high quality size specific silica sand for use in their molding and casting operations. Green sand is a mixture of 80 to 95% high quality silica sand, 4 to 10% of binders such as bentonite and limonite, 2 to 10% of carbonaceous additives such as coal dust and wood flour, and about 2 to 5% of water. Green sand is not green in color. The term green refers to the sand that is moist or wet in the mold when the molten metal is poured into it. The preparation of molding sand is a key process determining the final quality of casting products. The important requirement of molding sand is that it should possess all the characteristics needed to produce defect-free castings. To achieve that, the molding sand should possess certain properties such as flowability, green strength, dry strength, hot strength, permeability, refractoriness, adhesiveness, collapsibility, fineness, bench life, coefficient of expansion and durability. Testing of molding sand. Modern foundries strictly follow a test program for control of the sand system. The type of tests to be performed on a routine basis and their frequency depend on the nature of production, type of sand system used, sources of raw material and complexity grade of castings produced. The casting defects arising from the sand can be prevented by conducting appropriate tests to measure the various properties of the sand. The Bureau of Indian Standards has recommended a set of parameters to test the foundry sand. They are grain fineness number, moisture content, permeability, total clay content, strength of the sand, wet tensile strength and hardness. Grain fineness number is a standard parameter to express the size of molding sands. This number is calculated from the size distribution, which is determined by a set of sieves made as per ASTM standards. For good compaction sand, the amount of sand retained on 3 or 4 consecutive sieves should be in the range of 75 to 80%. The grain fineness number is considered to be proportional to the number of grains per unit weight. Moisture content test is used to determine the percentage of moisture in the molding sand. Modern foundries use the moisture teller apparatus to rapidly assess the moisture content. The amount of acetylene gas which is generated when water and calcium carbide are mixed and react, and that is directly proportional to the amount of water present in the sand. The results of moisture percentage are taken from a pressure gauge. Low moisture content in the molding sand does not develop the required strength properties, while high moisture content decreases permeability, so striking the right balance is important. The permeability of the molding sand is tested with an apparatus known as permeability meter. Permeability is expressed in terms of permeability number, which is defined as the volume of air in cubic centimeters that will pass per minute through a sand sample of 1 square centimeter cross section and 1 centimeter high at a pressure of 1 gram per centimeter square. Clay content tester is used to calculate the total clay content in the molding sand. Clay is the percentage of particles with a diameter of less than 20 microns in the molding sand sample. The molding sand is agitated in water to separate clay from sand particles, enabling removal of the clay which remains suspended in distilled water at room temperature. The wet tensile tester is used to accurately determine the tensile strength of the condensation zone in a clay bonded molding sand. This instrument recreates the mold environment at the mold or metal interface by utilizing a heater to generate a condensation zone in the sand specimen. This instrument is fully automatic and displays the wet tensile results in an easy to read digital display. Foundries that are facing difficulties with casting expansion defects can benefit greatly by including wet tensile results in their sand control efforts. A universal testing machine is used to test the strength of the molding sand. The sands that can be tested are green sand, dry sand or coarse sand. Different tests like compression, tensile, shear and transverse are used for sand control purposes, but the most common of these is the compression test. A standard cylindrical sand specimen of size 50 mm diameter and 50 mm length is used for testing the strength of the sand.
The surface hardness test of the molding sand is carried out to determine the density of ramming of the molding sands. The spring-headed spherical indenter, which acts like a plunger, penetrates the mold surface, and the depth of penetration that has been calibrated in terms of hardness units measure the hardness of the mold.
Core making is a process that forms the interior cavities or recesses of the casting. A core is defined as a portion of the mold which forms the hollow interior of the casting or a hole through the casting. The core is a full-scale model of the interior surfaces of the casting. The core is inserted into the mold cavity before pouring the molten metal. The molten metal flows and solidifies between the mold cavity and core to form the external and internal surfaces of a casting. Based on state or condition, the cores are classified as green sand core, dry sand core and no bake sand core. The types of core based on nature of core materials are oil bonded core, resin bonded core, shell core and sodium silicate core. Based on the position and shape, the cores are classified as balanced core, cover core, hanging core, wing core, ram up core and kiss core. The types of core based on the types of core hardening process are carbon dioxide process core, hot box process core, cold box process core and oil no bake process core. Based on the production requirements, the core making processes such as cold box process and carbon dioxide process are used in PSG Foundry. Cores are surrounded by molten metal and the core sand has higher requirements compared to mold sand in terms of strength to support their weight and the buoyancy force of the metal, permeability and collapsibility. The ingredients of the core are core sand and binders such as core oil composed of linseed oil, resin, light mineral oil and other binding materials. The function of a core binder is to cement the grains of sand into the desired shape and to impart sufficient strength to cores to prevent breakage, distortion and erosion in the core making, molding and casting processes. Mullers are used for mixing the sand and binders to distribute the ingredients into a homogeneous mixture. The muller generally consists of a cylindrical pan in which heavy rollers roll in a circular path about a vertical rotating shaft. After mulling, the core sand is discharged through a door located at the base of the machine. Cores are shaped in core boxes which are used in the same way as the patterns that are used to form sand molds. The core sand mixed with a binder is filled into a core box either manually or using core shooting machines. The excess sand in the core box is removed using a strike-off bar. After sufficient ramming, the cores are carefully removed from the core box without any defects for further processing. In recent years, modern foundries use carbon dioxide gas for hardening the cores. Carbon dioxide gas is passed through the core sand mix containing sodium silicate as the binder at a pressure of about 1.4 kg per centimeter square. The sodium silicate present in the core reacts with carbon dioxide and gives out a substance known as silica gel. The silica gel is a hard substance like cement which helps in the rigid binding of sand grains. The process is highly productive. The core produced by this process has higher compressive strength but poor collapsibility. For higher productivity, core shooting machines are used, in which core boxes are mounted in the machine and sand is pressed into the core box under a stream of high velocity air at a pressure of about 6 to 8 kg per centimeter square. Due to the high velocity of air, sand is passed instantly into the core box. These machines can accommodate up to a maximum of 150 kg of sand and multiple core boxes along with pallets and produce different types of cores in a single setup. The core box has several vent holes suitably located so that as the sand is introduced, the air is ejected through these vent holes. These machines can reduce the overall cycle time by 28 to 36% and facilitate the production of high quality, defect free cores. After the cores are made, they are transported to electric core ovens for baking to dry the moisture and to harden the binder. The temperatures used for baking may vary from 150 degrees Celsius to 400 degrees Celsius depending on the type of binder used, size of the cores, and the baking time. In modern core ovens, dielectric heating is used for high quality cores. The core oven should be equipped with adequate control of temperature so that the correct temperature can be maintained according to the type, size, and shape of the cores. After baking in an oven, the cores are properly finished by the following operations: trimming, brushing, muddling, and coating. Trimming involves rubbing of cores with emery stone. It is required to remove the loose pieces and other undesirable sand projections. Brushing involves filing for removal of loose sand with the help of a smooth wire brush. Muddling involves the localized coating of graphite or red talc to fill up any cavity, rough spots, and joining lines of assembled cores. Coating involves depositing a layer of refractory or protective material which improves the core's heating resistance. It is applied by swabbing, spraying, or by dipping. The aqueous carrier-based refractory coating must be dried in an oven after application, and the organic solvent carrier-based refractory coating, which is self-drying or can be ignited and dried by its own combustion. Graphite refractory materials are most commonly used for coatings in iron foundries and non-ferrous castings. Intricate core shapes that are made in 2 or 3 pieces are required to be joined before placing them in a mold cavity. Core paste, a mixture of talc, dextrine, flour, molasses, water, and other ingredients, is applied at the localized core surfaces to facilitate the joining of such pieces. Core making is an essential part of today's foundry operations. Cores play a significant role in the production of the internal surfaces of the castings as required by manufacturing industries in a wide variety of applications.
Molding involves packing the molding sand uniformly around a pattern placed in a molding box. A good casting depends on a good mold. Today, as requirements for casting products become more and more stringent, high quality molds with the right dimensions, hardness, and strength are absolutely critical for the consistent production of high quality castings. PSG Foundry uses both conventional and machine molding to produce castings as per the customer requirements. Conventional molding method is used for making medium-sized castings at PSG Foundry. A cast iron box called the mold flask is used in this method. The mold flask is usually of a 2-piece type, namely cope at the top and drag at the bottom. The mold flask is used to retain the molding sand, and it must be rigid so that there is no distortion during ramming of the sand or handling. The flasks are very heavy, so they are kept on the foundry floor for molding. This process is also called floor molding. The cope flask is set on the drag with high precision to ensure that the mold halves go together without distortion of sand and cores. Once the molds are ready, they are transported safely to the pouring section using overhead cranes. Generally, the surface of the green sand mold used for producing medium or heavy castings is washed or sprayed with plumbago refractory coating. It contains the graphite particles of size 75 microns mixed with carriers such as isopropyl alcohol. The graphite in plumbago will not melt at the highest foundry temperatures, but its carbon is driven off by oxidation at these temperatures depending on the air available at the metal and mold interface. After application, the plumbago is burnt off or torch dried to evaporate moisture from the surface layer of the rammed sand to a depth of 8 mm to 25 mm. This thermal hardening process increases the strength of the mold. Machine molding is best suited for mass production. It reduces manual operations, fatigue of workers, and increases productivity. Jolt squeeze machines operated using compressed air are used for packing the molding sand in a flask. These machines can perform both jolting and squeezing action. In the squeezing action, the flask filled with the molding sand is squeezed against the pressure board pneumatically or hydraulically until the mold attains the desired density. In the jolting method, the flask is first filled with the molding sand and then the table supporting the flask is mechanically raised and dropped in succession. Due to a sudden change in inertia at the end of each fall, the sand gets packed and rammed. The combination of both jolting and squeezing actions gives good compaction of sand near the pattern as well as on the top, where the squeeze plate comes in contact with the mold. Green sand molds are often dusted by graphite powder or talc powder using a molder's dusting bag to achieve better casting surface finish, greater ease of cleaning castings, and less casting defects. The horizontal parting flaskless molding machine ensures reliable and stable mold production. All molding sequences are carried out in a single workstation. High quality and consistency are achieved using a unique aeration sand filling technology. Low pressure air fluidizes the sand to fill the complicated edges and pockets in the pattern with sand for more accurate results and ensures uniform sand filling density. An automatic drag shuttle mechanism has been adopted for a safe and comfortable setting of cores and molds. A horizontal flask molding machine along with an automatic mold handling system is used for producing high quality medium and heavy near net shape castings. This molding machine can make 100 to 150 molds per hour. Before the flasks move into the molding machine, the interior and top surface of the flask, pin, and the bushes are cleaned thoroughly. This feature ensures the smooth operation of the line and helps to improve the mold quality. The molding line starts with a separating unit, setting the cope and drag flask on the molding line. The emptied flask pair along with the pallet car will be transferred to the mold conveyor and lifted to separate it from the pallet. Meanwhile, the gripper unit moves up and down and front and back to separate the cope and drag flask and transfer to the molding machine. The hopper is mounted with load cells which stop the sand feed as soon as a pre-programmed weight has been reached. The flaps below the hopper open up and uniform sand distribution will be ensured. The cope and drag are filled with molding sand one after another in the same station using an automatic pallet changer. The finished molds are handled by transfer stations which ensure good motion control along the molding line. The rollover devices are specially designed to avoid sand spills on the mold. The excess sand on the back of the mold is removed by a heavy-duty sand cutter. The robust flasks are designed to withstand the high-pressure forces during blow and squeeze, ensuring that the precision of the mold is maintained even after the forces are released. A very robust mold punch-out completes the system. The mold is punched out from the lower side, so the mold is pushed up. This gives safe handling of the castings on their way to the shakeout. By lifting the molds, the shakeout can be positioned at floor level for easy access to the castings by the operator.
Recap. In this module, the second of the 5-module series, inside a modern foundry, 3 important production-specific aspects of PSG Foundry have been described. Foundry sand is critical in creating the actual mold cavity that holds the molten metal when it is poured. Various additives impart the required characteristics of foundry sand. The automatic sand plant at the PSG Foundry facilitates a continuous supply of sand of requisite quality to the further downstream processes. Wherever the finished casting has recesses and cavities, cores are used to prevent the molten metal from entering these cavities, thus acting as fillers or spacers to leave a cavity in the casting. Cores need to have certain characteristics of their own and have their own manufacturing process sequence. With all the elements in place, the 2 halves of the mold box or flask, namely cope and drag, are ready for assembly in order to receive the poured molten metal. The molding line in a foundry is similar to an assembly line in an automobile plant with a series of mold boxes ready for the melting and pouring processes. This is followed by furnace charge preparation, melting and actual pouring of the castings, which will be covered in module 3.